So, hello, my name is Hartmut Grote. I'm a professor of experimental physics at Cardiff University, and my background is in laser interferometry, mostly gravitational wave detection. But we also have a research program to search for fundamental physics with laser interferometry, and that is what this talk will be about. So, there are two main topics here: dark matter and experimental quantum gravity and very high frequency gravitational waves. I start with dark matter. Dark matter is well motivated, and there's a number of candidates for this. Traditionally, WIMPs, for example, that have been searched for a few decades now without success. So in the last decade, ultralight fields such as axions, scalar fields, dark photons became more viable candidates. And so a number of experiments went into the direction of searching for these. So I'll start here with light scalar fields and their connection to laser interferometry. This is a GEO600, a gravitational wave detector prototype facility in Germany with 600-meter long arms. So we see beam tubes here, which essentially is a Michelson interferometer. And our work here for scalar field dark matter is related to the fact that we realized, for example, here together in a work with Evgeny Statnik from 2019, that there's a dominant effect of scalar field dark matter if it exists on the beam splitter of a laser interferometer. So first of all, if ultralight scalar fields would exist as extension to the standard model, then they would make fundamental constants. For example, the fine structure constant oscillate at the Compton frequency that corresponds to the dark matter particle. And that would be true for all objects, so all objects would change size and oscillating in size at the Compton frequency of the scalar field. If the dark matter in our galaxy, for example, would be composed of this scalar field. And so this was realized a while ago. However, in this work, we realized that the dominant effect is on the beam splitter here, because the beam splitter is asymmetric. It's this piece of glass depicted in the upper right here. One side of that is coated with a dielectric coating that reflects half of the beam. So that's the beam splitting surface. And if this object oscillates in thickness, then it would oscillate around its center of mass, and so effectively this reflecting surface would oscillate back and forth, and that makes a differential effect in our Michelson interferometer. So what we did then is to search in existing data of the GEO600 gravitational wave detector for signatures of the scalar field dark matter, which would manifest mostly as a single line in the frequency domain, and one would know one signature, which is that it should have a line width of about 10⁻⁶, which has to do with the velocity distribution of the dark matter in our galaxy. So we devised kind of an optimized search method where we do an FFT, fast Fourier transform of the data, to have a near optimal line width for all frequencies. So in the normal typical FFT, you have the same line width at all frequencies. But for this search, for very light field dark matter search, we optimized it such that at each frequency, we have a near optimal bin width of 10⁻⁶ of the search frequency, which corresponds to the line width of this hypothetical field. And so here's a spectrum of the number of candidate lines we ended up with, which are a lot, but we could rule them out either because they were not stable in time, or their line width didn't correspond to the expected 10⁻⁶. So we could set new upper limits with this work. Here we have an upper limit exclusion plot with a coupling constant per GeV. And in this work from 2021, we set new exclusion limits based on this GEO 600 search for scalar field dark matter with this green region, which are a few orders of magnitude better than former existing experimental limits. So which nicely demonstrates the power or sensitivity of this interferometry. Then we did the similar analysis with existing data from the so-called holometer, where this is a setup of two Michelson interferometers with 40-meter-long arms that existed at Fermilab in the US. The same principle here, the beam splitter would be moving back and forth. This was constructed to search for signatures of quantized space-time. I'll talk about that in the second part, and is discontinued now, but we also analyzed the data, and that gave this red exclusion plot here, so with a new exclusion region at some higher frequencies. And then we also did this just recently published last year for LIGO data, where we also took the effect onto the arm mirrors into account. And so one can argue that, so the first argument was the effect in size thickness changes of the end mirrors of such an interferometer cancel out because they are roughly the same. But then if we take small differences into account, can be an effect, there's a small effect as well. So we incorporated that here and further improved the analysis method a bit. And so we could set new limits with LIGO here below a few hundred hertz in this new exclusion region. Okay, so these three, these were not really tabletop, of course, just to illustrate the sensitivity of laser interferometry for dark matter searches as an example of fundamental physics you can do with laser interferometry. But that also applies, of course, to tabletop. So I'll come back to that a bit later. So let's move to tabletop experiments. And there is a new class of tabletop experiments that searches for axions. And we have one of these in our collaboration. So that's the QI, Quantum Enhanced Interferometry collaboration in the UK, which is part of the Quantum Technologies for Fundamental Physics program in the UK. And so in this, we have a ring cavity setup on a tabletop. Here on the right-hand side is the image of this. So that's a long optical table, and here in isolated is the beam tube where a laser beam goes in a ring with a round trip length of about 10 meters. And so what this does is it searches for hypothetical axion field in the galactic halo, composing hypothetically the dark matter. And it explores an effect that the axion field would rotate the polarization of a propagating laser beam as the beam propagates. And so we have a large pump field here of more than 100 kilowatt in the horizontal polarization, for example, in blue, which goes in a circle here. And then while it propagates, its polarization direction would be shifted. And then this shift would oscillate at the Compton frequency, and then this polarization which shows up in the orthogonal, in the S polarization, which carries the signal of the axion field, would be detected here at the output. And so this already works quite well. So with this, we could set new upper limits that reach or that go close to, they're not new, but they get very close to existing upper limits from the CAST experiment at about a mass of 2 nano electron volts. So it nicely demonstrates this new principle in tabletop axion search experiment with laser interferometry. There exist 2 other ones as well, one in Tokyo and one at MIT. Okay, with this, I move to the second part about experimental quantum gravity and very high frequency gravitational waves. To start with quantum gravity, there have been long ideas that space-time is quantized at the very small levels in the sort of space-time form, for example. So hypothetical space-time fluctuations, maybe at the Planck scale. If they were at the Planck scale, then they would probably not be accessible to experiments for quite a while. However, if we assume a holographic principle, which many physicists do, then with some additional assumptions, this may be accessible to laser interferometry. So in a nutshell, the holographic principle is the statement that the amount of information in a volume can only be as much as the information you can fit on the surface of that volume. And so that can lead to correlations between different regions in space-time in their fluctuations. That's the assumptions. And these could be explored with laser interferometry. So the first experiment to try to go this direction was the holometer at Fermilab, which I mentioned earlier, consisting of two Michelson interferometers that are called co-located, just meaning bringing them as close together as you can in space. But they're independent Michelson interferometers, and so as light propagates in these arms, it would collect a random walk style phase shift from space-time fluctuations. And because of the vicinity of these two interferometers, these space-time fluctuations would be correlated between the two interferometers. So you take the output stream of the two interferometers and cross-correlate them in time. So searching for cross-correlated noise between the two interferometers. That's the idea. The Fermilab holometer set some upper limits with this for quantized spacetime, and it's discontinued now. But then we started in Cardiff 2018-19 the QUEST experiment, quantum enhanced spacetime experiment, that takes this idea to the tabletop scale. And so while you lose some sensitivity if the experiment is smaller, we gain the flexibility of a tabletop. And we also compensate for less sensitivity with advanced technologies like higher power and squeezed light, so that in the end we can be more sensitive than the holometer and also more flexible in terms of modifying the experiment. So right now this is the only tabletop co-located highly sensitive interferometer that is built for this surface. So its main science target is quantum gravity, but because it's so sensitive, it will also be sensitive for scalar field dark matter coupling to the beam splitter, as explained earlier. And naturally, it's also sensitive to very high frequency gravitational waves. So here's a layout of the QUEST experiment as it exists today so far. Two power-cycled Michelson interferometers. So we have beam splitter with the Michelson arms. These are 1.8 meter long right now. And we have a power cycling mirror that enhances the power to 10 kilowatts in a year or two from now as the main target. And then here's the readout, and then the readouts will be cross-correlated. So here's a current view. There's the vacuum chambers here. We see the two arms in the background here of the two Michelson interferometers. This box here is a squeezed vacuum source to enhance the quantum noise of the interferometer. So we have first results from a first science run that we performed about a year ago, which are published. So these are typical sensitivity curves we use in interferometry, depicting displacement per square root of Hertz, or amplitude spectral density, in displacement units over frequency. So our sensitive range here is a few megahertz to 80 megahertz right now, which is given by the tabletop scale. And then in blue and green here, you have the individual displacement sensitivities we achieved of the two interferometers in our first science run from last year at around 5 times 10 to minus 18 meters per square root of Hertz. And this flat part here is all dominated by the quantum noise. So at the limit of the theoretical performance for a given light power of about 100 watts in each interferometer. But then you see the beauty of this technology of cross-correlation with the red curve. So we cross-correlated these two interferometer outputs for about 10,000 seconds, and that gives the combined sensitivity, the red curve, so at a few times 10 to minus 20 meters per square root of hertz displacement sensitivity. And so this is a limit for cross-correlated stochastic noise between the two interferometers that would be kind of stationary in time, as a quantized spacetime signal would be, or stochastic gravitational wave signals would be. So we didn't find any cross-correlation here, which is indicated by this intrinsic noise here, which behaves as uncorrelated noise. But also we have other measures for the correlation. So we didn't find any correlation yet. And so we could make a new upper limit with this already, which is kind of an auxiliary result, if you will, given by the high sensitivity of laser interferometry. So it's not a new quantized spacetime result, but what is new and published last year is that we can set a new upper limit for a very high frequency gravitational waves with this in the range from 13 to 80 megahertz, where there existed no real experimental limits, broadband limits before. In the lower left here, you see the holometer gravitational wave limits in strain from the past. And in our final configuration, we can reach about the same sensitivity for very high frequency gravitational waves as the holometer, but over a wider frequency range. So in the future, we try to increase the arm length of this Quest experiment. So we have a nice 6 by 6 meter optical U-shaped table where we want to move the experiment in the next within the next 2 years. And we are also adding a different quantum technology, which is single photon readout. So it can be shown that single photon readout for this type of Michelson interferometry can be beneficial over the standard quantum readout for stochastic sources, which is a new idea. Yeah, we will try to add that and also possibly change the geometry of the arms, which has to do with predictions for quantized spacetime noise that we can test. So within the next years, on the 5 meter scale for the Quest experiment in this new lab and on this table, we can test actually predicted quantization of spacetime signals. Okay, I want to finish with that and just show our group on a recent outing. So in the experimental gravitational wave group in Cardiff, we are 3 faculty right now, 2 postdocs and a number of PhD and master students. And we do have a postdoc positioning mostly experimental gravitational wave quantized spacetime physics right now for our Quest experiment. So please contact me if you like, and then I look forward to seeing you in the discussion session. Thank you.